So welcome everybody to our today's colloquium. To remember you, this is the joint colloquium between the Goethe University Frankfurt and the Universidad Nacional Colombia in exchange of recent research in atmospheric science. So for today we have three speakers. We will start with Lorenzo Giovannini. Then we will move to the presentation of Weinkaemmerer, and we end the event with Manuel Zuluaga. So Lorenzo, the floor is yours. So you can start to share the screen. So Lorenzo is an assistant professor from the Department of Civil, Environmental and Mechanical Engineering from the University of Trento, and today he will talk us about the extreme precipitation events over the eastern Italian Alps, the role of large-scale forcing and local orography. So Lorenzo, you have 15 minutes, a little bit more than 15 minutes, so the floor is yours.
Okay, thank you. You should see my screen.
Yes.
Okay, thanks for your kind invitation and for this presentation. Today I will talk about extreme precipitation events over the Eastern Italian Alps, and in particular I will focus on the storms that usually occur during the autumn months in the southern part of the Alps, so in the Italian side of the Alps. And I will try to evaluate what is the role of large-scale forcing, so synoptic conditions, and then also the effects of local orography, in particular in locally shaping the precipitation field. In particular, I will talk about two different events, which are the most important events in the last 100 years over the Eastern Italian Alps. The first one is the so-called 1966 century flood, which is very famous, at least in Italy, and for sure the most, we can say, important flood in the 20th century. It occurred between the 3rd and the 5th of November 1966. It caused the death of 118 people, and in particular, it was characterized, as we'll see later, by extreme amount of precipitation in 2 days, with peaks of the order of 750 millimeters, which caused the overflow of different rivers in Tuscany and also in the northeastern part of Italy, in particular Arno, Adige, Ombrone, and Tagliamento rivers. And as you can see from these historical pictures, there was floods in different Italian cities, including Trento, the city where I live, and also Florence, with important damages also to the cultural heritage. And then due to the very strong southerly winds, which usually, as we'll see later, characterize this kind of storms, so sirocco winds, there was the highest surge ever registered in Venice, with a value of 180 centimeters above the average sea value, as you can see here in this bottom left figure. This is the first event, and then we will analyze another one, which we will see is very similar, in particular as the synoptic situation. This is a more recent event, which occurred more or less 4 years ago, between 27 and 29 of October. So as you can see, it is more or less the same period as the previous flood. In this case, 16 people died. Also in this case, extreme amount of precipitation, peaks around 800 millimeters in 3 days, and overflow different rivers in northeastern Italy, so in particular the Piave and the Brenta rivers. Here I report, just to start, the precipitation field accumulated during these two events. On the left, the 1966 flood, and on the right, Vaia. And you can see that the precipitation pattern is similar, with the maximum here in this pre-alpine region. Here we have the Eastern Italian Alps. Here we have the Adriatic Sea. I don't know if you're familiar with the region, but usually, in these cases, we have southerly winds, so humid wind coming from the Mediterranean, in this case, in particular from the Adriatic Sea. And the first reliefs that they encounter are the pre-alpine reliefs here with this orientation. And of course, due to this, the uplift of these southerly winds, we have the most important precipitation, so orographic precipitation on the southern slopes of the Alps. So you can see that the precipitation pattern is very similar between these two events. And this is due to the fact that, of course, also the synoptic situation is similar. Here I will show you some animation of the synoptic situation starting from the geopotential height at 500 hectopascal. And as you can see, again, comparing the two events, we have the deepening of a trough between France and Spain in both situations, with, as a consequence, strong southerly winds towards the Italian Alps, and as a consequence, the development of strong orographic precipitation. So you can see that the synoptic situation, of course, is not the same, but is very similar, and it is characteristics of this kind of events during autumn over the northern part of Italy. The same, more or less, can be seen from these other animations, showing in this case, the equivalent potential temperature at 150 hectopascal, and then the sea level pressure. In particular, here you can see the development of a low pressure on the western part of the Mediterranean, which then translates towards Italy, of course, connected to the trough that we have seen in the previous animation. And so you can see, in particular, in the Via storm, very well-developed warm part of the front, and then the passage of the cold front at the end of the two events. And finally, in these two animations, you can see the transport of water vapor. In particular, in colors, you can see the total column water, while the arrows represent wind field at 1000 hectopascal. Again, you can see the strong transport of water vapor coming from south, in particular the southeasterly wind preceding then the arrival of the cold front in both situations. So from this animation, you can see that, of course, the two events are not the same, but at least they are very similar. So the dynamic and the synoptic dynamic is very similar, with the deepening of a trough on the western part of Europe, and then a very strong southerly flow with, of course, the transport of water vapor and moist air, and then at the end, the passage of the cold front. And then the two events are similar also concerning the presence of an atmospheric river. Atmospheric river can be defined as a long, narrow, and transient corridor of strong horizontal water vapor transport that is typically associated with a low-level jet stream ahead of the cold front of an extratropical cyclone. And here in this figure, you can see just an example of an atmospheric river with this strong integrated water transport, which is ahead with respect to a cold front, so in the warm sector of an extratropical cyclone. And there are several characteristics of an atmospheric river. In particular, the position should be poleward of 20 degrees, the length higher than 2000 kilometers, the integrated water vapor higher than 20 kilograms per square meter, and the integrated water transport higher than 250 kilograms per meters per second. And these characteristics were present, we can say, in both situations, so both in the 1966 flood and in the Via storm, as can be seen from these two images. I didn't say, but all these, in this case, all these analyses were taken from ERA 5 reanalysis. And so you can see that we have these long rivers, and in particular, we have a long-range transport of water vapor coming from the tropical Atlantic Ocean in both cases. So you can see that in these two episodes, we have both, of course, a local source of moisture, which is the Mediterranean. So we have both the local evaporation from the Mediterranean, which is triggered by the presence, again, of this trough between France and Spain in both cases, as you can see again from these maps. But then we have also a long-range transport, so we have a contribution of water vapor coming from the Atlantic Ocean. So also in this case, we have a similarity between these two extreme events. And then in order to better analyze these two episodes, we also run simulations with the weather research and forecasting model for the two events, in particular with the same settings for the two events, with 3 two-way nested domains with 1 kilometer in this inner domain, which cover the area of interest, which is the eastern Italian Alps, 61 vertical levels. And here for for the physics scheme, I report just the PBL scheme, which is a Universität State University scheme, and then the microphysics scheme, so WSM6 microphysics scheme. From the simulations, we can have other, of course, animation just to show better the, again, transport of water vapor from the Mediterranean. In this case, I showed just for Baia, so just to show you again with the closest view, we can say the strong advection from south, and then the passage here of the cold front that can be seen here from the precipitable water, but more or less the same can be seen also looking at the equivalent potential temperature at 925 hectopascals. So again, the very strong advection of moist and warm air from south here, from southeast in particular, and then the passage of the cold front at the end of the storm. Here, of course, we validated in a quantitative way the simulation. Here, due to lack of time, I just show you some qualitative evaluation of the simulations. In particular, here I report the accumulated precipitation over the whole event for the 66 flood. The background colors represent the output from the simulation, while the dots represent measurements from different rain gauges. And of course, we have the same color scale. So it means that if we have that the color of the dot is the same as the color of the background color, we have an agreement between model results and observation. Otherwise, we have some errors. And it can be seen that in general, the model is able to capture the distribution of precipitation with the maximum I said before along the pre-alpine range. Of course, there are some errors, but in general, we have a good agreement between observations and simulations. And more or less the same can be seen also for Baia. We have seen before, more or less the same pattern of precipitation, which is mostly orographic. In fact, over the plane, we have, we can say, normal precipitation, while extreme precipitation is present just over this pre-alpine range, and then again, a decrease of precipitation in the inner part of the Alps. And as I said before, I don't have time to enter into too much details of this validation, but we can say that in general, the performance of models reproducing this kind of events is good. Because these kind of events, there are different studies in the literature, have a good predictability because they are caused by very large waves, and as a consequence, the synoptic forcing is very clear, and the models are able to well capture this synoptic forcing. And so generally, the general pattern of precipitation is well captured for these kind of events. Then we'll see later then that there can be also some local effects and local mechanisms, and in this case, it is more difficult, of course, for the model to capture local effects, while the general picture, we can say, is better captured. And now, in the last part of this presentation, I want to talk a little bit about these local effects. In particular, I will focus on banded orographic convection, which is typical, again, of this kind of storms which occur during autumn in the eastern Italian Alps. Here I present just some snapshot of the radar images for the Baia storm taken in the last part of the Baia storm, where I think it is clear the development of these bands of convection, which are triggered in particular by the first pre-alpine reliefs. In both images, you can see more or less the same situation. Of course, we don't have radar images for the 1966 flood, so we don't know actually if the same banded convection occurred also in the 1966 flood, but this is rather typical in general of this kind of storms, and this is just an example of another event which is not examined in this presentation, but just a year later, so in November 2019, you can see that we have more or less the same pattern with wind from southeast, which trigger these bands of convection, which can cause extreme rain rates downwind with respect to the beginning, to the starting point of these rain bands. So these are very significant because they can cause extreme precipitation where, of course, these bands are located. So we decided to study what are the thermodynamic conditions which can cause the development of these rain bands, and also which is the interaction with the local topography. We performed a lot of simulations. Again, here, due to lack of time, I just show you some analysis. In this case, we performed, again, with the Wolf model, numerical simulations, but in a semi-idealized setting. And so, as you can see here, we put a simplified ridge in the east-west direction, and we evaluated the development of banded convection with the wind impinging directly from south. So we used 3 nested domains with a resolution of 0.5 or 0.2 kilometer in the inner domains, and we evaluated also the sensitivity to the resolution, and here I cannot show the results of this sensitivity. And we initialized these simulations with the sounding from Udine during the firestorm. So in the last part of the firestorm, when the rain bands developed. In particular, Udine, because Udine is located here, so upstream with respect to the eastern Italian Alps. So it is an ideal location to evaluate the characteristics of the flow impinging on the Italian Alps. And then we applied random temperature perturbation in the range of 0.1 Kelvin in order to trigger convection. This is the SQT diagram of the sounding which was used from Udine for the initialization of the simulations. You can see that it's characterized in the lower part of the troposphere by moist instability. We have a moderate CAPE of the order of 700 joule per kilogram. And we have that the level of reconvection is at low altitude, around, as you can see here, 870 hectopascal. So, of course, there are suitable conditions for the development of convection. So, as I said before, we performed different simulations. These are the results of a control simulation with the control sounding. In this case, I'm showing the rain liquid mixing ratio at an altitude of 2,000 meters above sea level. I didn't say, but this ridge has an altitude of 1,500 meters above sea level. So we are more or less 500 meters above the top of the ridge with this plot of the rain liquid mixing ratio. And this was just to see if the model was able to simulate the development of the rain bands. And as you can see, these are 2 different hours, consecutive hours from the model results. And you can see that the model is able to simulate this particular convective mode, even with a smooth ridge. So just with the thermodynamic conditions and the temperature perturbation, it is able to develop this particular mode of convection. It means that the thermodynamic the sounding that we used as a thermodynamic condition, which of course are favorable for the development of this kind of convection. And here I report just a section in the west-east direction, so in this direction along the ridge of the vertical velocity in color and of the cloud liquid mixing ratio with the dotted line. And just to show that we have the development of these rolled vortices, so we have these rolls, and so these alternation of updrafts and downdrafts, which are characteristics of this kind of convection. And you can see that here the height of the updraft is rather elevated, so we have rather deep convection. And this is different with respect to other similar studies which are present in the literature, which evaluated mostly shallow convection. Here on the right, we have a cross-section, but in this case, along this band, so in the south-north direction, in colors, we have again the cloud liquid mixing ratio, while with the lines, in this case, we have the vertical velocity, and just to show the development of this cloud triggered by the presence of the slope. Then, as I said before, we perform a lot of different sensitivity analysis. I just show you the result, the sensitivity to thermodynamic conditions. So with respect to the control sounding, we varied the stability. So with a more stable sounding and a more unstable sounding in blue and in red, to evaluate the difference then in this case, in the pattern of convection, in this case again, I'm showing the rain liquid mixing duration. Sorry. Okay. And in the case with a weaker instability, so a more stable sounding, we can see that the bands develop, but they are weaker. And in particular, we have a more stratiform, we can say, precipitation, so less convection. While in the situation with more instability, we have that the mode of convection is changing. And in particular, we have the passage from a more banded convection in the control simulation to a more cellular convection. So we can say that for development of bands, we have to be it is needed a certain amount of instability, otherwise we don't have a good development of banded convection. But the profile should be not too unstable, otherwise we have the passage to another mode of convection, so we have the passage from a banded convection to cellular convection. And then we repeated also other experiments with even more unstable sounding, and there was the passage to a complete cellular mode of convection. And finally, we performed simulations varying the topography, so with different perturbation of the topography, in order to evaluate the effects of the topography in triggering this kind of convection. So in this case, we perform simulation with orographic perturbation, but without temperature perturbations, and with just small topographic perturbation in the range between 0 and 50 meters. We have, yes, development of bands, but not so well defined, we can say. So also in this case, a more stratiform precipitation, while with perturbation of topography in the range between 100 and 150 meters, the bands are well developed and fixed, triggered by specific bumps of the topography. And the last simulation, sorry, there is also this one, but yeah, I'm running late. I can just skip this and just show you the last slide. We then performed a realistic simulation of the VIA event. So realistic in the sense that we put the real alpine topography and with again the input sounding coming from the Udine weather station, and it is clear that of course bands developed inside the model, and these bands are triggered by specific bumps in the pre-alpine orography. As you can see, there are different bands which are triggered by these bumps in the pre-alpine orography. So similarly to these perturbations that we have seen here, also the perturbation, the natural, we can say, perturbation of the alpine orography are acting in triggering these rain bands. And of course, this is very important because there are specific locations where the formation of rain bands is favored with respect to other locations. So in conclusions, we analyzed 2 extreme precipitation events occurring during the autumn months over the Eastern Italian Alps, which are generated by a specific synoptic pattern with the deep troughs over Western Europe. We've seen that in these cases, we had also a significant contribution from atmospheric rivers. So we have both a local source of moisture and a long-range transport of moisture. We then reproduced these events with the Wolf model at 1 kilometer resolutions. And we've seen that these events are generally well reproduced. So there is a good predictability of these events, in particular of the general pattern, we can say, of the precipitation distribution. Then there are some, of course, uncertainties. These uncertainties are mainly connected to the development of local convection. And in particular, we have seen that one of the convection mode, which is typical of these events, are rain bands. In fact, the thermodynamic conditions are generally favorable for the formation of rain bands during these autumn storms. And these rain bands can cause extreme and localized rain rates, which, of course, as a consequence, there can be potential hydrogeological problems. Okay, thank you. Sorry, it was a little bit longer than expected, but yeah, this was all from my side. Thank you.
Thank you, Lorenzo, for that very nice presentation. So somebody has a question?
Yeah.
Okay, I can start. Lorenzo, I found it very interesting, this thing of the local effects. So you, in this simulation, so what is happening there? So this is only the real topography, but with the profiles that you show it from Udine, isn't it? So,
yes.
And this is how much is the resolution of this topography? I mean, this is the same 200 meters, something like that?
In this case, it is 1 kilometer. So it is actually more or less the same setting, so the same topography that we use for, well, these real simulations. But in this case, just using always the same the same boundary condition, we say the same sounding coming from the Udine weather station.
Okay, so that means that when you say that it's local mechanisms, they are local because of the topography, but that doesn't has to be like a very high resolution. I mean, the 1 kilometer topography, it's well enough to.
Yeah, I didn't show here, of course, because I didn't have time, but yeah, we perform the same simulations, in particular the idealized simulations at 1 kilometer resolution, 500 meters and 200 meters. And we did not found important difference. So the model was able to simulate the rain bands with the same spacing, the same characteristics at 1 kilometer, 500 meters, and 200 meters. So it seems that with these kind of thermodynamic conditions, the model is able, even at 1 kilometer, which can be, coarse, we can say, or at least not to fine resolution, but it seems able to simulate this kind of bands, which actually, at least in this case, they have a spacing of about 10 kilometers.
So Daniel, I think you have a question.
Yes, thank you, Lorenzo. Very, very interesting presentation. I have two questions. The first one is regarding these two extreme events that you looked at. I guess they are kind of uncommon because they are extreme events, so they don't happen all the time.
We hope.
Yeah, we hope that they won't become very common in the future. But then this synoptic configuration that you mentioned, is this more of a more common condition that you can find every winter or every autumn?
Yes, yes, you're right. In the sense that actually this synoptic configuration with trough deepening over Western Europe is rather common, and it is present, we can say, more than one time every autumn. We can say that the typical period is between October and December, more or less. And of course, in these cases, the extreme event came from the strength of this trough and the temperature contrast. In particular, in Vaia, there was development of a very strong low pressure at the surface, which probably was triggered also by the fact that the Mediterranean was warmer than the normal. And then in these two cases, but not only in these two cases, we have also the transport of water vapor from the Atlantic. So we have also this contribution. Actually, I didn't show also this, but we performed also some sensitivity tests, changing the boundary conditions in both events. So evaluating actually the same storms, but without the contribution of water vapor from the Atlantic. Some actually blocking the water vapor coming from the Atlantic. And we saw that, yeah, of course, there was an important decrease of precipitation because part of the contribution was from the tropical Atlantic.
Okay, thank you. And the other question I have is regarding your idealized simulations. Mm-hmm. Do you think the distance between these rain bands could that be maybe resolution dependent in your model?
No, well, this was one of our concerns when we started this analysis, and for this reason we tried. We analyzed the data from this domain 2 at 1 kilometer resolution, and then with the domain 3 at different resolutions, so 500 and 200 meters. And actually, we found that the spacing was not dependent on the resolution. And we were happy because that was one of our concerns. We also performed a Fourier analysis of the signal to evaluate the peaks of the signal, and actually the peak at the 3 different solutions was exactly at the same place.
Okay, thank you.
Oh, you're welcome.
Very nice.
Very good. So again, Lorenzo, thank you very much for your presentation. So now we will be moving to our next speaker today. It's Ian. So Ian is a last year PhD student from the boundary layer meteorology group at Goethe University in Frankfurt. And today he's going to talk about the turbulent slope winds in complex terrain, from heat and moisture transport to the sampling of single plumes. So Jan, the virtual floor, it's yours.
Yes. Yeah, it's really going from synoptic scales to really small scale now. So I hope it's in presentation mode now.
Yeah, it is.
Okay, then hi and welcome to my talk, and thanks for the opportunity to present. And yeah, I'm talking a bit about some intermediate results from my PhD project, and the title is Turbulent Slope Winds in Complex Terrain, from Heat and Moisture Transport to the Sampling of Single Plumes. So first, an introductory slide. So I'm focusing on the convective boundary layer over mountainous regions, and on fair weather days in an alpine valley. I think you can imagine that it yeah, it looks somehow like this, and so we will have an onset of convection and a formation of a slope wind circulation. So this is what you see in the drawing on the right hand side. So we will have anabatic winds over the slopes, upslope winds, and then a recirculation into the valley with local subsidence in the valley center. And of course, there's also cumulus cloud formation possible over the ridges. And this is my main point on this slide. So in a regime like this, the transport is realized both by turbulent fluxes, and these turbulent fluxes include also the plumes, and by plumes I mean hot air updrafts in the boundary layer. And on the other hand, there is a non-local transport, so there's the advection by the slope wind circulation, which is forming in the cross valley direction. So, and at first we did some idealized LES studies for process understanding on a simplified case like this. And yeah, that's because we were interested in the mass transport between the surface and the free atmosphere in complex terrain. So this can mean the export of moisture out of the valley, for example, which is important for cloud formation, or you can interchange the moisture with pollution or CO2 or some other tracers, or tracer dispersion in general. So we performed some idealized LES studies with a simple orography using the CM1 model, and then we did a detailed budget analysis. And what I have plotted here is the moisture budget, so the moisture tendencies in the valley cross section. So from left to right, it's the total tendency. So basically, the red color means a gain in moisture, and blue colors mean moisture, a loss in moisture. And in the middle, it's the contribution from the slope wind circulation to the moisture tendencies, and on the right hand side, the contribution from the turbulence. And what we have found out is that in case, so for the moisture export, or in general for the export of a scalar of a tracer, yeah, the slope winds are quite dominant. So there's an efficient moisture export by the slope winds out of the valley. So which this arrow shows here. And yeah, the slope winds are the dominant process for the vertical moisture transport here in this case. And now in our next step, we have switched on an upper level wind. So as I said, up to here it's quite idealized. So before we haven't had some synoptic forcing. So and then we found out that a large scale upper level wind, which blows in cross valley direction. What it does, it mixes the moisture from the slope wind layer, from the moist slope wind layer into the dry air over the valley center. And this leads to, over one diurnal cycle, this leads to a significant moisture, significant reduction of moisture export. So the moisture export is considerably reduced. So this is the U4 case, that's an orange dashed line. So I'm talking about the right-hand side panel. It's about the moisture export, and yeah, as you see, it's strongly reduced for this upper level wind case. And what we also found out is that, in contrast to that, the heat export is much less affected. As yeah, okay, the sentence is a bit and this is what's described in our first paper here. But now if you think of NWP models, for example, then the problem is that these boundary layer processes are not resolved on the numerical grid, and normally they get parameterized in NWP models. So if we go from a typical LES resolution on the left side panel to a more NWP-like resolution, then you see that this slope wind circulation, more or less disappears, but it doesn't disappear completely, and this is the problem here. So we run into the so-called gray zone problem. So that's that over a certain range of resolution, the boundary layer features are neither completely subgrid nor fully resolved. So and furthermore, it's the problem that the existing boundary layer parameterizations do not account for any subgrid orography, which is not resolved at a certain resolution, or for differences in turbulent statistics between mountainous terrain and flat terrain, especially in combination with thermally induced winds. So we needed some better insights into the turbulent statistics over orography, and that's complicated because it really goes over many scales. So besides this thermally induced wind, which contribute to a non-local transport, we also have the thermal plumes, and they also contribute to vertical exchange by non-local transport. So into our LES model, we implemented some sampling method to identify the plumes, and to study their characteristics and to get some statistics, and hopefully to get an idea how to improve the boundary layer parameterizations. And this is how this a result of this sampling looks like. So this is the green surface is the one side of, as it's a valley slope basically, and over this slope you see this three-dimensional surfaces. So it's these are the plumes, these three-dimensional structures, and the more red a surface is, the higher is the vertical wind speed. And on the backside plane shows, so it shows the projection of the horizontal wind. So you see this blue region, it's the recirculation into the valley center. And the arrows on the, it's a bit hard to see, but the arrows on the surface is a 10-meter surface wind. So yeah, how did we do this this sampling? So that's it's a bit technical now. So basically we set up a reference case which is quite simplified at that stage. So it's a moderately deep valley, a 20-kilometer wide valley. It's infinitely long and it's periodic, and it has constant surface fluxes and no upper level wind in this case, and there's basically no cloud formation. And then we implemented a passive tracer at the surface with a decay at some decay rate, and then we applied this sampling method, and it's basically a threshold condition for every grid point. So if the tracer concentration anomaly exceeds some threshold, so it's in some way the standard deviation of the tracer concentration, then a certain grid point is accounted for, as part of a plume. And then, of course, based on this information or on this data, we wanted to compute the turbulent fluxes. And for the flux computation, we also need, we need turbulent flux like this, so this A prime, B prime. To compute it, we need ensemble average, and this ensemble average is it's computed by, on the one hand, by spatial averaging along the valley axis, along the y-axis, and by temporal averaging over 40 minutes in this case. And now we can decompose the ensemble average further into the slope wind circulation and the overall domain average. And furthermore, we can decompose the turbulent flux again into three single terms. So into the part from the plume, so the organized turbulence part, so the plume part basically, and then the turbulence going on in the outside of the plume, so in the environment, and some in-structure variability. So this decomposition is called top hat representation. And for the turbulent heat flux, so W prime theta prime, this decomposition for our two test cases flat, so without any orography, and our reference case with the idealized valley looks like this. So on the upper row, you have the part from the plumes, and then the environment around the plumes, and then the in-structure variability, which is quite small. And these three add up to the turbulent flux in the lower row on the left, on the most left panel. And then for the reference case, or for the idealized valley, we have additionally to that, we have the flux by the circulation, so by the slope in circulation, and in total this gives the total heat flux. And from this decomposition, we see that this the plumes really dominate this the heat flux, and also the moisture flux, which is not shown here, the turbulent moisture flux. So they're really crucial in this for these processes. And now we can dig a bit deeper into this into the statistics by computing the so-called joint probability density functions, or joint PDFs, of the turbulent fluxes at different heights. So basically the joint PDF is this function P here, and meaning that integrating over the probability density function gives back the value for the turbulent flux, or for A prime, B prime. And based on our sampling data, we can now get, on the one hand, the total flux and only the plume part of the total flux. And yeah, this looks like this. And furthermore, we can do a quadrant analysis, so defined by the sign of the turbulent interaction in each. So it gives us 4 quadrants, and for scalar quantity, this means that in the first quadrant, so that's a positive times positive interaction, so a positive vertical wind perturbation times a positive potential temperature perturbation. This is where, in this case, where we can find the plumes. So that's called ejections here. So this basically means that warm air rises. Yeah. So it's can think of it as a plume in the lower part of the boundary layer. And then there, of course, there are 3 more quadrants, so which are called outward interactions, sweeps, and inward interactions. And now this is how these joint PDFs look like for the flat case, or for a flat boundary layer over flat terrain at 4 different heights. So so it's each height is a quarter of the boundary layer height. So, and we see that in the lower part of the boundary layer we have the turbulent flux is consisting mainly of the plume contributions. So the black part here of the density function is really dominant here, and the positive correlations are dominant. And at higher levels, this is kind of the other way around. So there you can imagine that at the top of the boundary layer you have overshooting plumes. Yeah, and so up to here this is known basically, and now this is how this looks like for our reference case of the idealized valley. So, and here our perspective is that the circulation, so the slope wind circulation, the slope winds, is basically all subgrid. So these statistics are referring to the domain average. So which basically means the domain temperature average and the domain vertical wind average, which is basically 0, of course. And so, and the yellow areas here are the contributions from the slope wind circulations. And you see that there's some overlap with the plumes, of course. And so the lowest height level here, it's down in the valley basically, and this is the valley mixed layer, and this is qualitatively still similar to the flat boundary layer, at least qualitatively. But then at higher levels we are kind of cutting the slope wind layer with the plumes, of course, and the valley center where we have the subsidence of the recirculation. And this is above the ridge tops, so it looks quite different. So as a short summary, we have shown that this conditional sampling of plumes works successfully over this idealized valley, and we have seen that the statistics between the flat case, also between the flat boundary layer without orography and our reference idealized valley case, is quite different, the turbulent statistics, and it's also the case for the turbulent moisture flux, and only have shown the heat flux here. And especially at the ridge height, where you have kind of stationary updrafts over the mountain tops, but of course only a few because it's on the mountain tops. And now this information, or this we can think of using this PDFs in a PDF-based boundary layer parameterization. I would say the the final goal would be to adapt the boundary layer parameterization for orography. So, for example, you can think of the assumed PDF method, and of course, it also needs to be extended to a cloudy boundary layer. And I would say our next step would be to go to further semi-realistic simulations over real three-dimensional topography, and yeah, which gives this nice flow patterns on the 10-meter levels. So yeah, that's it. So I'm open for questions.
Thanks, Ian, for the very nice presentation. Somebody has a question? Okay, so maybe I can start. Ian, so you say that you make the comparison with the NWP resolution with 5 kilometers, something like that, in the same case, isn't it? So which parameterization are you testing there?
It was just a remark. So
okay.
This basically this plot is from a paper, and it's without parameterization. It's just showing that it was just for illustration to show that it's
okay. So what it's losing there. So the idea, so the natural next step, as you say in your conclusions, it's to try to include this into a parameterization. And do you have an idea of how to do that?
Well, so I mean, I would say the most promising maybe would be to yeah, as I say, to take some PDF based method and to adapt the PDFs for orography to include some subgrid orography features. And yeah, of course we have to test it first over some 3D topography and do some LES simulations first to see how these PDFs look like in a 3D topography, because this plots which I've shown here is only over the 2D or kind of 2D idealized valley. So, but the
phenomenon seems to be 3D, isn't it?
Yes, it's 3D, but the valley it's quasi two-dimensional, so it's at an infinitely long valley, if you like. So it's quite simplified. So yeah, but yeah, so it's. I mean, I would say that would be the final result at the end of my PhD, maybe to give some hints or some idea to how to do it, maybe, but. Yeah, it's only a bit. It's only the first step, I would say. Yeah.
Great. Thank you, Ian. I think that Daniel has a question.
Yes, thank you, Jan. Very interesting. So yeah, this boundary layer turbulence is always a big issue. Which do you think would be the minimum resolution that you would need to be able to simulate these blooms in the boundary layer? Do you think you can do it? I don't know.
Not too high. So we have did some sensitivity tests for the resolution, and it's so 40, 50 meters. It's for most features, it's actually enough. So it's I mean, it's already a high resolution, but
yeah,
not.
Okay, yeah, because I get we have similar issues with convection, which is already above the boundary layer, and if we really want to resolve these thermals of the blooms in convective clouds, we also need something like at least 100 meters, something like that.
Yeah, something like
it's
that.
Similar, yeah.
Yeah.
Okay, thank you.
We have another question from Alejandro Martinez. So he says, congrats for the talk, and that it's possible to say that the models at NWP resolution are underestimating the vertical transport of quantities compared to LES?
Yeah, I mean, it depends. In principle, yes, but it depends. I would say it depends on the boundary layer parameterization. So, of course, without any boundary layer parameterization or subgrid without any subgrid model if it would be heavily underestimated. But yeah, you could. Yeah, it really depends on your choice. So yeah. So there are boundary layer models which tend to overestimate something and some tend to underestimate something. So it's yeah.
Okay, so Jan, thank you very much again for your presentation, and now we will move to our last speaker, Manuel. Manuel Zuluaga is a researcher at the Department of Geosciences and Environment from Universidad Nacional in Medellin. And he will talk today about orographic controls over convection in an Inter-Andean valley in the northern South America. So Manuel, the virtual floor is yours.
Thank you. I hope you're seeing my presentation correctly.
Yeah, it's perfect.
It's perfect. Okay, thank you. Yeah. Okay, thank you I'm Daniel for inviting me. I mean, for me, it's a pleasure to give this talk in this group. I mean, this is kind of the first time I give a talk in this area of the world. But what I'm showing you here is some of the results of this research that, I mean, has been conducted mainly in the master thesis of Sebastian Gomez. So we work hardly to produce this, and it's currently reviewed. We're producing a paper in the monthly weather review for an upcoming publication. So I'm going to talk about basically how the topography imposes control on the convection in the northern South America, in the Valley of Colombia. So I guess what motivated us to perform this study is this question. I mean the question of how and why convection manifests so strongly in this region, in this north part of the South America, especially here in the northern fringes of the Andes, or where the Andes ends in northern Colombia, close to the Panama region, especially where the ITCC, the Intertropical Convergence Zone, interacts with the topography. So here we have seen that the topography and the convection interacts between them to produce different types of convective elements, from deep convective towers, I mean, pretty strong, pretty intense, with a lot of lining, and then to morph into wide areas of intense precipitation. These areas are what it's more likely, well known to mesoscale systems areas that even reaches, a really, really greater sizes to broad stratiform regions. What we know is that the orography, of course, is what imposes controls on the energy exchanges produced by the tropical circulation in these hot and humid areas, of course, nearby the two oceans, the Caribbean here on the north and the Pacific to the west. So this is what basically determines what is the relaying processes, the rain-related processes in most of the valley. So one of the most important for us is the Andes themselves, of course. The local circulation in these valleys, of course, are really important, are small, but are needed to be considered in order to understand what is going on in the outcome of the precipitation. And basically, another motivation. Oh, sorry, my Microsoft Word just crashed. I'm sorry.
No worries, you can start again.
What is going on? I'm gonna stop sharing. Wait a second. Sorry, everything crashed. So I'm so sorry for this.
Don't worry, it's Microsoft's fault.
Yeah, sorry, it's an older version of Microsoft, so I guess I need an update, an upgrade of this. Okay. Let me start again. Oh, gosh. Okay. Okay, please don't crash on me. So just to finalize my motivation, and I hope you're seeing again what this motivation slide is that I mean, convective system in this area are not only important for the rainfall that they produce, but also they are linked to a lot of extreme rainfall events with intense wind gusts, significant floods that most likely produce a lot of the emergencies that we experience in these narrow valleys. So so basically the objective of this work is try to explore the relationship between the orography and the observed convection in this Inter-Andean valley, located in the northernmost south part of South America. We have two questions that are posed here to give solution to this objective, basically, which is how the atmospheric environment associated to the convective systems. I mean, how is the environment, and how this can be related to the orographic configuration of the terrain that you see in this area. And another question is basically, if the terrain were different, so if we change the terrain, obviously it's a hypothetical scenario, but there will be any changes in the atmospheric outcome that are associated with the systems. So for this, to give this answer, so we have basically the following strategies. So we use a diagnosis of the convection, just to give an overview of what is going on in the region. Then we are going to analyze a study case through simulations using the weather and research forecasting model for trying to reproduce the observed precipitation on the region. And finally, we are going to explore the atmospheric outcome, just doing some hypothetical scenarios, modifying the topography within the model, just to kind of advertise the paper that we are trying to put forward. Is going to be, I mean, basically all the conclusions of this paper are going to be compiled in this publication, hopefully shortly. So the Magdalena Valley. So this is the study region. So just to give a little bit of geographical context. So this is a region, a special region where we can find a maximum on the precipitation. I mean, in this region, in this tropical region close to Colombia and Panama, there is a maximum of the precipitation, but especially over the ocean. I mean, this is a warm and humid ocean, but inside the valleys, there are also a maximum of the precipitation, and that's where we wanted to focus our analysis, is how to understand how these maximum of values that are really comparable to the maximum to the west, how they are produced, and what are the controls that the topography imposes on there. So the Magdalena Valley is located in the northernmost region of Colombia, is the largest river of the country, is basically aligned, is this valley here between the central ranges on the eastern ranges, and it's aligned north and south. Another importance, I mean, and to show how important is the valley for the country itself, is that it covers about the 25% of the entire area of the Colombia, and it has, I mean, basically the 80% of the population has interactions with what happens within the valley. So it's really an important modulator of the precipitation and basically the outcome of what you're seeing within basically the central part of the Colombia. So the analysis is performed based on simulations using the WRF model. I'm not going to say anything about the model, since I guess many of us are familiar with this widely used model, but the only thing I'm stating here is that we use a pretty standard configuration. We use 3 domains, nested domains. The higher resolution domain is about 3 kilometers. And we initialized the simulation with the GFS final analysis. for the parameterizations, we use a pretty standard way of parameterizing a convective resolving model. But we try, I mean, since we wanted to explore how the microphysics reproduces the observations, we explored 3 configurations on the microphysics. So we ran these experiments to try to get the best results comparing to the observations. So here I'm showing you the simulated rain rate for the period of the study. This is average over the central Magdalena Valley, so basically over this area here. We ran the model for about 10 days, just taking care to select kind of a drier period at the beginning and a really active period with intense precipitation also, just to give a contrast with what happened with the drier and wet periods. So the lines in these figures corresponds to the black line is the observation, so the satellite observations, and the other 3 lines are the solutions using the different parametrization. The model performance, what we see is that the model performance is, I mean, it's acceptable, showing this well-known feature of this solution. When we run solution with the WRF, it's a little bit of overestimation compared to what you see on the observations. But since we want to try to reproduce or to select the model configuration that the best reproduce the observed, we found that the Thomson scheme, so running the model with this microphysical scheme, will give us the best temporal correspondence despite the overestimation of rainfall. Just to also basically show that the model is able to reproduce the diurnal cycle, all of the 3 configurations reproduce fairly acceptable what do you see in the diurnal cycle, because we're also interested in exploring what happens with this. Here I'm showing you a little bit of what happens with the distribution of the energy fluxes within the area. So here I am showing you an evolution in time of the meridional, zonal, and the precipitation for 3 selected regions. We selected 3 regions because we want to describe what happens in this region. Since, I mean, first the valley is kind of aligned north-south, and the sequence of events that happens in these 3 regions are closely related to the dynamics of the entire valley. So for the northern regions, so this region here at the north, you see, so here is the meridional wind in this shaded time series. So you see a down valley southerly wind followed by a northerly wind and a kind of a up valley wind. So basically pretty standard, a strong diurnal cycle within the study period. So within these 10, 15 days that we were simulating. The black line, dashed line is the precipitation. So you see basically a strong diurnal cycle, a little bit of change on the zonal wind within the maximum values, but it's pretty standard, or it's pretty, I mean, pretty consistent on the diurnal cycle. Now, what occurs in the other 2 regions is really, I mean, it's a little bit different, basically. So in this middle region, I mean, even though there is a diurnal cycle, the diurnal cycle is not so well, is not so kind of alternating as what you see on the northern region. So you see a more consistent, strong southerly wind, like a kind of down valley wind from the north, especially in the drier regions, in the drier periods at the beginning of the simulation. But when the rain starts to peak on the region, you see these intrusions of northerly wind here on the for the region, basically. And the south, that is basically this down south here, is more, I mean, is more kind of is more different. It's completely different from what you see on the north. So you see this, basically there is no northerly wind, and only when there is rainfall, significant rainfall events, you see this intrusion of northerly wind basically to help us just to pick up the rainfall on the area. So what is going on in here is that for these important rainy events in the M and S region, what we see is that there is a kind of an influx of moist influx from the northern region, and this is in these figures. I mean, just to confirm what you just mentioned, is that so the first figure, this is a Hofmöllers of the meridional wind, specific humidity and divergence along this transect, and basically that follows the approximate alignment of the valley. So you see again the strong diurnal cycle, basically in most of the variables. But when you are seeing these peaks on rainfall, you see these strong intrusions of moist air from the north. So basically, what is going on is that to occur rain on these areas, you need this influx of moisture, of extra moisture, basically to pick up from the environment and produce the outcome of the precipitation. Another way to show this is just if you separate the analyzed period from dry and wet days and daytime and nighttime periods, basically to separate what happens when there is no rainfall and when there is rainfall. And since there is a strong diurnal cycle, you separate what happens in the day and night. So this shows here are maps of rainfall on the top and wind vector and specific humidity on the bottom. Basically, what you see for the dry days, for these periods where there is no significant rainfall within the valley, basically there is this southerly wind, so this Don Valley wind, and it's relatively bringing kind of a drier air over most of the valley, and probably that's what is basically preventing the rainfall to occur within the valley. Now, when you contrast this picture with the rainy periods, you see a completely different picture. So you see, of course, you select the rainy period, so the rainfall is increased within the valley, and the fluxes completely change. So you see now this basically the southerly wind is completely removed. Now you see more, and especially during the night, this northerly wind that is kind of bringing this extra supply of moisture. And one characteristic that is interesting in this area is that this southerly wind, this northerly wind is not only northerly, but also has a westerly component. So basically, it's pushing masses of air towards these slopes to the eastern or to the western slopes of the central Cordillera here, and basically what is enhancing the precipitation within, and especially during the night. And one of the just to mention something, the peak in rainfall in this area is at night. That is kind of a different from the picture of the continental areas where you see the peak in rainfall in the afternoon. So what we're seeing here is that the shape of the valley, or basically the configuration of the valley, has to do with the location of the timing of the maximum rainfall in this area. Just to kind of show a different view of the same analysis is if you do a vertical cross section that shows basically the wind vector, the horizontal and the vertical wind vector, and the relative humidity on the shading in these figures. Basically similarly to what I showed you before. So the dry days, the dry periods are on the bottom, and the rainy periods are on the top, and for daytime and for nighttime. And I mean, not only you see that there is kind of a basically the picture that you see here is a kind of a disorganized flow around the valley for this, especially for these days where there is not much rainfall, or where there is not much intense rainfall. However, for the rainy periods, the flow organizes and basically follows the east-west configuration of the valley, and then is kind of pushing areas of moisture and wind towards the western slopes, and of course, I mean, the outcome is going to be intense rainfall. So finally, I'm going to show you a quick glance of the other type of experiments that we run, basically to explore changes in the atmospheric variables when you forcefully modify the topography on the model. So we want to make these exercises basically to assess kind of the sensitivity of these atmospheric variables when you change this fixed parameter that is the topography. So we expect that with these solutions, will help us understanding what are these relative processes that are modulating the occurrence of rainfall in hypothetical scenarios. So we ran three more experiments. So control is basically what I just showed you before, just the real case, and we ran basically three more experiments. One including a blockage on the northern region, including a barrier, and another experiment, sorry, combining, and another removing the central valley, just to try to explore what happens with if you widens this area, so you remove the entire central valley, and a middle experiment where you combine the both two. And these are the results. So this is the accumulated rain for each of these scenarios. Basically, in the same simulation period we analyzed before. In black line, we include the control run. This is the accumulated rainfall, and the three solutions using the modified topography. So just looking at the color lines, the blue and the red, not surprisingly, the inclusion of the barrier of the north reduces significantly the accumulated precipitation within the valley. So at the end of the simulated period, we reduce kind of more than 50% of the rainfall. Basically just reducing the availability of water vapors inside the valley. But for us, what is interesting is the changes on the outcome of the precipitation when you basically widens the valley. So first of all, none of the observed simulations were able to reproduce this peak in rainfall, this big event that you saw before on one of the earlier figures that I showed you. So basically, the actual configuration of the valley is needed to produce this kind of observed simulation. Sorry, this kind of observed rainfall, and also, and I think is another important thing, is that the diurnal cycle completely changes when you introduces these changes on the topography. So the red case, that is basically the blockage, you reproduce basically the same peak in rainfall, of course, with less magnitude on the accumulated rainfall. But when you change the shape of the valley, basically you change the timing of the occurrence of the maximum precipitation. And is this valley, the northerly, like the removal of the entire valley, that changes, from this later time, or this midnight peak, to an earlier time, to a late afternoon peak in rainfall, which is more consistent with what you expect in the diurnal cycle of a continental region. So basically, so what this implies is that the actual shape of the valley is necessary to produce not only the observed elements of precipitation, the intensity of the precipitation, but also to reproduce the actual timing of the rainfall, or when they occur, which is what, as I say, maximizes on the night. Basically, in other words, the actual shape of the topography is what strongly explains the outcome of the precipitation across the region. And just to kind of finalize my talk, I'm just going to give you some of the conclusions that we were just kind of posing in this analysis. So we ran some high resolution experiments to describe and analyze this dynamical lower atmosphere troposphere in this Inter-Andean valley close to, I mean, in the Magdalena Valley. So we found that the model basically they resemble fairly well the observations when we use the Thomson microphysical scheme. I mean, I have run several other experiments using the same strategy of using different microphysical schemes, and always Thomson is the one that gave us the best results with the observations in these areas of the tropics. So the model results also shows a strong diurnal cycle with maximum of valley winds during the rainy and nighttime hours of these periods, and maximum down valley southerly winds during daytime hours. The model also suggests that enhancement of the northerly winds that coincides with the occurrence of enhanced precipitation is what basically brings up this extra moisture to the area, just to get this outcome of intense precipitation that is observed in this area of the tropics. And finally, just to, I mean, the terrain modification experiment that we ran suggests that the diurnal cycle is strongly attached or is strongly dependent on the actual shape of the topography. And right now we are running some other experiments just to try to kind of reinforce this conclusion, because I think this is one of my early questions was always how to explain this nighttime peak in rainfall in this area. And with this, I am open to receive any questions. And hope everything.
Thank you, Manuel, for this nice presentation. And somebody has a question? Yeah, I think Daniel has a question. Go ahead, Daniel.
Thank you, Manuel. Sorry, I have some connection issues here and I had to switch to my mobile phone. But yeah, this is really a very interesting question about this nighttime peak in convection in the Magdalena Valley. It has always troubled me as well. And I think you really show very nicely, first, that it has to do with this northerly winds coming into the valley. But then I guess the next question is, why do these northerly winds only occur at night, or mostly occur at night, and create this? And then I guess this has to be linked to the topography, because that's what you showed with the simulations where you removed the other mountain range. But how do you have like a simple mechanism that could explain that, why these northerly winds only occur at night?
I guess I don't have an explanation, and that was one of the questions posed by one of the reviewers when we tried to kind of bring up this article for publication. And so we try to explore a little bit of the synoptic configurations around the day, because I guess I mean, as you saw on the north, there is a strong, I mean, like this diurnal cycle. Basically, what you expect to find in a coastal region in between an ocean area and inland area. So, but it looks like there is when there is maybe a wave activity is associated with the easterly wave. This, I mean, the setting of the wind start kind of imposing this northerly or basically this northerly component that is basically imposing its synoptic configuration to give the observed what we observe in these rainy periods. But one of the thing is that not always when you see an easterly wave activity, you see this northerly wind. So maybe there are another issue that I'm not sure what is going on in there. So there is probably has to do with the convections on the west. Basically, when the Chocó with the Pacific coast of convection start to pick up, there is a strong system there. This is like the system that covers really wide areas. I mean, sometimes half size of the Colombia in the ocean area. Maybe those can modulate anomalies on the wind, but that's a hypothesis that we haven't kind of explored yet. So I guess it's just synoptic configurations. I don't think that is more like local. It could be also kind of reinforcements on the rain. So rain starts to happen in this region. Big systems occur, produce deepens or basically reduces the geopotential or reduces the pressure, and also probably also helps to favor the intrusion of this or of this northerly wind into the region. But I guess that's the next question that we wanted to solve with more analysis in this area.
Yeah, thank you, Manuel. Yeah, I think this is really exciting, and there's still a lot to find out in this region. Yeah, thank you.
Any further questions? Okay, maybe I can place a question. So, Manuel, you showed that in the diurnal cycle, when it was assessing the performance of the model, you showed that in the cumulative rain, in that picture, it looks like at the beginning of the afternoon, the model has a hard time to reproduce what it's happening there, like it's too rainy. And you said in your conclusions that the rain events are driven by the orography. So have you tried to increase the resolution of the simulations to see if this thing can match a little bit better? It's because of that or not?
We haven't. I guess that's one of the. I mean, we started doing these simulations quite a while. So when we didn't have so much resources to run all of these experiments, but we must increase the size of the resolution. But also basically I don't know if the model imposes at this diurnal cycle, because basically that's imposed by the initial conditions, by the boundary conditions, or it's just the model itself trying to reproduce what is going on. My guess is the second, because if you change the topography, the model completely changed the diurnal cycle. So the model is not trying to kind of a climatological diurnal cycle. It's trying to reproduce it, but you have a good point. I mean, these maximums on rainfall in here, I mean, like that is not observed on this minimum, what you see of the observation. So I guess the model has to do. There is something in there that is not entirely correct when the model is kind of performing in this area.
Manuel, Joanna has a question.
Hi.
Hi, Joanna.
Manuel. Thank you for your presentation. It was very, very great. In connection with the question of Daniel, you make a very interesting point about the Chocojet, and I think it's very, very connected with the northerlies that we are having. You are having in your simulations, because in my PhD dissertation, I don't know if you remember, but we found in our simulations that when the Caribbean low-level jet was entering about for the Panama Bight, and then it goes west, right, and then turning like northerlies. So it's very, very interesting to see if there is some kind of connection with this northerlies.
Yeah, and I think that's the solution, because what you're seeing is when you see these maximums in rainfall in here, you see a wrapping of the wind around these northerly tips of the Andes on the north of Colombia. So basically, when the rainfall maximizes in the Chocó, so there is a kind of a extension of this wind that wraps around what we call the Betulia and the region of northern Antioquia, basically. And that's the way that, I mean, that's one of my hypotheses. I haven't explored it yet. I just saw it in different synoptic configurations. But that's one of the things that we're exploring to see if we can basically solve Daniel's question on what is the driving of this northerly wind. And you made a good point, Joanna. Thank you.
Thank you.
Okay, so again, thank you very much, Manuel, for the presentation and all the speakers as well. So for those that maybe are interested, we plan to upload this colloquium online. So yeah, that will be soon in some platform, and we'll let you know by email where it is and how to find it. So again, thank you very much. I guess that I'll see you in our next event that will be in a few months from now. So we'll let you know by email. So thank you very much.